Good morning, everybody. Okay, today is what should I say? Is the second lecture. Okay, second formal lecture on quantum finance, and today's topics is we're talking about very interesting topics on the quantum field theory for quantum finance. So first of all, don't be so worried. Okay, basically I will give you some basic concept and also the introductions on the quantum field theory. So what is quantum field theory? And what is the basic component? And what is the meaning of different component? And also the most important part is how it can relate to quantum finance. Okay, what my requirement for this course is not a mathematics course, okay, or on quantum mechanics, but rather is how to make use of this concept, okay, onto finance, what we call quantum finance. So my requirement on the basic knowledge on the quantum field theory is basically discussed in this lecture. But of course, if you want to know a bit more details for this lecture, you can reference to my book, okay, which can be found from Amazon, of course, okay. Because in China, when you order books, hard copy, it takes a long time. So better you buy a Kindle book, okay, an ebook, that will come faster. But anyway, if you go through the my PowerPoint, okay, it's quite comprehensive, okay. And as you can see, and I won't focus too many on the equation, okay, but rather is on the basic concept, okay. So that part make clear, okay. So today in today's lecture, we focus on several different things. First, what is quantum field theory? Okay, what is that? And how it related to quantum mechanics. In fact, later on you will know that quantum field theory, although is very related to quantum mechanics, but they are two different kind of things. Okay, I'll talk about that. And how it related to quantum finance is the most important part. Okay, so today we talk about three things. So what is quantum field theory? What we call the QFT, and how it related to QM, quantum mechanics, and of course how it relate, okay, and correspond to quantum finance in terms of the basic concept theory. So first of all, take a very brief look, okay, on the quantum field theory. Okay, it's very simple introductions. As mentioned in my introduction, okay, quantum field theory is a major component in quantum theory, originate from the three major topics. First, quantum mechanics, and also on the theoretical physics with the integration of classical theory, quantum mechanics, and special relativity. So you can see quantum field theory, in fact, is a combined kind of a theory, okay, with the major component of course quantum mechanics, but together with classical theory and also special relativity. So it's filled into one. You can say something like this. So it involves many fascinating phenomena, what we call, as we have mentioned in the last topics, wave particle duality, uncertainty principle, and my favorite, quantum entanglement. So in this lecture and chapters, okay, first we will give a very brief history on quantum mechanics, okay, very interesting, I think. And then after that we will discuss the fundamental concept of several main quantum field theory topics that are related to quantum finance, and key foundation concept and understanding on quantum field theory. So first, very basic concept, okay, quantum mechanics in a nutshell, what we call. So, introduction. So quantum mechanics, in fact, is a kind of special topic, you can say, okay, in quantum physics, or what we call the quantum theory. Some people say, okay, it's the same thing. It's a theoretical physics, okay, which described the very basic nature of every single atom and what we call the subatomic particle. Okay, like the proton, neutron, electron, neutrino, that sort of thing. Okay, basic kind of what we call material or particles. So before quantum mechanics, the whole role of physics, as I mentioned in the previous lecture, is guided by two basic theory, okay, what we call laws. First, of course, the well-known Newton's law of motion, right? The first, second, and third law of motion that try to govern every single object in the physical world, okay, with what we call median size and median velocity, okay, normal thing, what we call the macroscopic object. The other theory, okay, govern the whole world, okay, is it exists, okay, but it's not solid in some sense, okay. That important law is what we call the Maxwell electromagnetic wave equation, which govern another kind of thing is two things: the electrical field and magnetic field, and the interaction in the physical world. So you can see the first law is talk about some solid object. The second law talk about some thing, okay, it's not physical, but it exists. In fact, it's very important, right? Electromagnetism. So two important laws. And quantum mechanics and other law is talk about some very small kind of basic component, okay, atoms and the what we call some quantum particles. Okay, they have different properties. So, for example, is a wave duality particle, as I mentioned beforehand, like the proton or like the electron. So sometimes it exists as a kind of atoms if you observe that. But and sometimes, okay, it exists as a kind of wave. So you have the diffraction, interference, and so on. So light is a very good example, right? Light as a kind of wave when we study optics, okay, using the Newton's optics. But if you learn, okay, proton, okay, as a kind of particles, okay, so it also have particle properties. And the second one is for that kind of subquantum particle, they have very special property, what we call quantization, which means it exists as a particular energy, momentum, or energy level, what we call. As you can see from an atom and the different electron, right? We will talk about this later on. Okay, so all the times, the magnitudes or sometimes the energies or energy level and momentum sort of thing, they exist, but not continuous. Okay, it's what we call discrete level. Okay, we call this quantization. That's a very special kind of thing. Because in the old days, we all believe everything is continuous. Velocity is continuous, times is continuous. And I remember the first day I joined the course on quantum mechanics at Hong Kong U. Okay, Professor Kosu asked, do you believe time is continuous or discrete? That's all. So they are limited to the precision with which quality we call this uncertainty precision, as mentioned in the last lecture. Okay, then what we call pairs. Okay, we'll measure again. Okay, today. Okay, we call these uncertainties. Okay, physical quality pairs. Okay, that you cannot 100% sure. Okay, they exist or their accuracy. Okay, but they exist, of course. And the last one is the most fascinating one is what we call quantum entanglement. Quantum entanglement is a very special kind of feature in the sense that the behavior of one subatomic particle can affect the other one, even they are separate in a very, very long distance. We say, for example, across the universe, something like this. Okay, we'll talk about that. Okay, and the most important part is not only fascinating, it has a large range of applications. We'll talk a bit about that. Okay, and as you can see from this chart is a very well-known chart for the hydrogen wave function with different energy state. Okay, without time we move on into details. Okay, of course, if you see the both, I will discuss a whole page talking about that. Okay, very interesting. Okay, so a brief history. Okay, in all my course for the book, all the times I will try to summarize. Okay, the major event or major person, okay, that affect the history of a particular kind of theory or concept, okay, or models. So for us, it's quantum mechanics. So we start with year 1803. So first one, of course, is Maxwell. Okay, Faraday. Faraday with his major, okay, contribution on what we call electromagnetism. Before that, we don't have that idea. After that, we have the idea in the universe, in the whole world, there exists something not solid, but it exists, very important, we call this electromagnetism. Very important theory. And also his major study also another thing is what we call the black-body radiation. In fact, it's a kind of birth of quantum mechanics. Although at that time they don't have that kind of concept, but it's the beginning. So the second most important scientist in the, of course, is James Clerk Maxwell. Okay, and the well-known what we call the Maxwell equation, if you know about this. In fact, it's one of the majors. Okay, and equations. Okay, and just like Newton's law of motion. Okay, it's very fundamental. And also, this equation, Maxwell equation, describes the formulation of the classical theory of electromagnetic radiations. Okay, so it's a very basic kind of constant theory. So after Isaac Newton. Okay, the third one is very important one. Okay, is a physicist. Okay, and also a philosopher. Okay, Boltzmann. Boltzmann, the major invention, okay, and also the theory is of what we call statistical mechanics. Statistical mechanics is a very important theory, and also for the what we call the second law of thermodynamics. Okay, is a very important theory to govern, okay, the chaosity of every single object in the universe. Okay, from order to disorder. We have time in the lecture we talk about that. Okay, one of the major behavior, of course, when we talk about quantum mechanics. And then, very important scientist, okay, because we have the Planck constant, is the Max Planck. Okay, Max Planck is a German scientist, okay, in the 1858 to 1947, during the First and Second World War. Okay, it's a Nobel Prize winner against, and the most important part is his major invention, okay, and discovery on the what we call quantize. Okay, and also, okay, it's one of the major contribution on the birth of quantum mechanics. Okay, at the end of 1918 and the beginning of the 19th century. So of course Einstein. Okay, of course Einstein is not a major contribution of quantum mechanics, but okay, his works, okay, on the electromagnetism, of course, okay, photoelectric effect is a very special kind of what we call demonstrations on how that kind of subatomic particles, okay, works. And also one of the important part, okay, is quantum hypothesis, okay, and also his several different major argument with Heisenberg, okay, is a very important event during the First and Second World War. And of course, one of the major contributors is Schrödinger. 1887 to 1961. In fact, the most important contribution is his own equation, right? Schrödinger equations that appear over 100 years, but still valid. Okay, and the most important part is we still make use of it. Okay, and this equation come into paper is, if I'm correct, is in 1921. Okay, at this 10 years very important. Okay, this 10 years we have for Einstein. Okay, his relativity. We have Schrödinger equations, and also we have Heisenberg. We'll talk about that. Yeah, Bohr. Bohr, of course, the most important part is the what we call the Bohr model. It's a very famous standard physicist. Okay, who main contribution of the atomic structure, and is quantum theory. Okay, how to calculate different kind of what we call energy level. If you study high school chemistry, you already know this. Okay, but maybe at that time you won't ask your teacher why. Okay, different electron appear in different energy state. Okay, and at that time, Bohr, okay, have a kind of what we call special theory of that. Okay, that is one of the major contribution on quantum mechanics and also structure of atom. Lastly, of course, is Heisenberg in 1932. Okay, proposed his major work. Okay, in fact, it's 1921. So you can see it's very close to Schrödinger equations. Okay, he published his papers. Okay, and talk about something what we call quantum mechanics. So you may ask, okay, Heisenberg in fact is the father of quantum mechanics, and also is the one who, okay, coined these terms in 1925. Okay, and of course, Nobel Prize winners for creation of quantum mechanics. And that particular theory, I think the most important part is that at that time, it's still a theory, but after almost 100 years, right? Okay, go through over 100 or 1,000 experiments. Okay, and every experiment proved that that kind of quantum mechanics or theory or phenomenon is true. So that's why it's so important. So which means when Hankin-Spray proposed this quantum mechanics and these of equations, okay, at that time it's only a concept. But after 100 years, okay, most of them already proved to be correct. So that's why it's so important. Okay, the basics, the wave-particle duality. Okay, I won't go through detail because last week we have already go through some. Okay, today I just give you some basic equation. Again, okay, don't worry, I won't. What should I say? I won't ask you the equation because it's not a mathematical course. Okay, but of course we have some very important equation, but not that. Okay, these are directly related to quantum mechanics or quantum field theory. But just to show you the basic equation. And two reasons. First reason, I will show you how elegant and simple the equation is. As I always say, the more important the equations or laws, the more simple and beautiful it is. Okay, but all the time it's very, very, what should I say, elegant in some sense. Okay, so the first one is the what we call the Maxwell equations. Maxwell equation important part is just like Newton's law of motion. It tries to relate two kind of things into one. So in the Maxwell equation, try to relate two totally different kind of things. One is the electric field, E field, and one is the right hand side, the magnetic field. Okay, and they are related in this beautiful equation. And again, it's true. So by doing that, we have invented many kind of things. Of course, electric engine, motor, dynamic, and try to solve different phenomena, very basic phenomena. So it's one of the most important equations. Of course, the second one is the Newton's law of motion. Newton's law of motion, we try to relate two kind of things, right? First, an object moving with a particular mass and acceleration, and that acceleration with the mass will come with the force. Okay, so again, it's very simple and elegant, you can see. Okay, symmetric in some sense when they compare with each other. But of course, they are talking about two kind of things, right? So we can say one is a physical world, one is the what we call a non-physical world, right? So something you cannot touch, but it exists, and all exists in fact. So wave-particle duality is talking about what we call as a kind of dual phenomena. Either it's a particle or a wave. So engulfed by very beautiful equation, what we call the Schrödinger equations. Okay, no worry, we will see that equation again and again. And most important part is, although it is the same equation, we have different format. Okay, the most genetic form is this format. Okay, it relates wave function. I'll talk about this in detail. Don't worry. Okay, and also what the correlations. Okay, with time. Okay, or without time. I'll talk about this later on. We have two kinds of Schrödinger equation: time-dependent Schrödinger equation or time-independent Schrödinger equation. And for us, we will talk about time-independent Schrödinger equation. I will tell you why later on. Okay, it makes everything more simple. Okay, so don't worry. And of course, we have talked about some basic phenomena. So, for example, what we call the back-body radiation. Okay, it's a very basic theory. Okay, and what we discovered years before, almost 100 years before, is for every single kind of object. Okay, say for example, a sun. Okay, whatever. Okay, and it will emit energies. Okay, but that kind of energy emission is not continuous. It's discrete. That is a very important observation. Okay, it's what we call back-body radiation. And the second one is, of course, we have already learned it, right? Okay, the wave particle theory, the double slit experiment. I will go through that again later on. It's a very interesting one. And the third one is very important one, of course, the what we call the photoelectric effect. Okay, is the major discovery by Einstein that crowned him for the Nobel Prize. So you see, for Einstein, okay, the most interesting one is although okay, his theory of relativity is so famous, okay, but he won the Nobel Prize not because of relativity. Instead, it's the most basic, not simple, basic effect, what we call photoelectric effect, which means, as you can see from this circuit system, okay, when you have electricity, okay, and then you have some, say for example, glow page, for example, okay, so it will emit some, okay, photon, okay, or whatever, electron, whatever, and it strike into a plate, okay, it will emit. When you shine a proton, it will emit some electricity. So what we are talking about is digital camera. Okay, is that kind of effect. Okay, so in other words, it's a kind of device that can emit energy from light. It's a kind of conversion. You can think about it. Just like E equal to mc squared. As I always say, they have different meaning. But for me, the meaning is how can you convert a pure mass into pure energy? That kind of relationship. In fact, it's a kind of conversion. You can think about it like that. Okay. As we are taking the higher energy physics, okay, that kind of E equal to mc squared, in fact, is the most basic equation. How to, okay, convert, say for example, uranium into pure energies, right? So in fact, it's a basic theory, okay, on that. So so you can imagine all the time the equation have different meaning. First, maybe just like F equal to ma, that kind of observation. But for F equal to m squared is in fact is a kind of conversion. How to convert some mass into pure energy if it can travel in the speed of light. So that's why we have E equal to mc squared. Okay, you can interpret like this. So you may ask, is it possible? Okay. Technically impossible. But theoretically it's possible. What? If you believe in the special relativity, you will know one thing, what we call time dilation. When an object increasing speed, it will become heavier and heavier. So basically, okay, and the limit is c, the speed of light. So if you want to increase up to speed of light, it will be so heavy that you cannot be further accelerated. So what I call is theoretically possible, but practically you can't do that. But for some you can. So for example, from CERN in Europe, okay, they can have, okay, what we call the particle accelerators, okay, using some subatomic particle, they can generate pure energies, okay. So that's how it. So such important properties clearly demonstrated in 3 important equations. First, black-body radiation, Planck's law, E equal to Planck constant, and also the frequency of the light. So you can see they are discrete. Okay, so this is what we call the Planck constant. Planck constant, in fact, is a very important and universal constant. Okay, we have several, of course, and V, okay, is the frequency of the black-body radiation. So you can see they are discrete, not continuous. So the second is the double slit experiment. Okay, we will go through it one again because it's a very fundamental and interesting phenomenon. Okay, it can describe many things. And the third one is what we call the Einstein photoelectric experiment. Okay, it's a very important. Again, it's a fundamental experiment. Okay, seems to be very simple, but in fact, it's very important. How we can, okay, generate electricity from light. So quantum finance, as we discussed in chapter 1, okay, we buy the concept is the major concept of the phenomena in the quantum world. So in other words, you buy the concept, also you buy the mathematical equations, right? So as I always say, all the time you have some physical model, and then within the model you try to derive some equations. So we actually we borrow the model of a quantum world, which means we borrow the non-leaf equations and formulation, of course. But again, don't worry. I've already tried to simplify all those equations into some what we call can be put into a computer equation, computer programs for calculation. So it's a different stuff. So principle of uncertainty, very first phenomena. So uncertainty principle, also what we call the Hankensberg uncertainty principle, is unique, and super important. So it is quite what we call the Schrödinger cat, as I mentioned in the first talk. Schrödinger cat is a very famous but hypothetical, and unique paradox, saying that the cat is a box with a force, and the force controlled by hammer, and the hammer, whether it will break into glass force, depends on radiation, trigger. So all the time it should be random, in some sense. So the beautiful thing for uncertainty principle is, how can we tell the state of the cat? So in terms of quantum mechanics, is either that of light, unless you open the box. So later when I talk about another very important theory, what we call the fuzzy theory or fuzzy logic. In fact, they have some very similar what I call of concept, and in terms of mathematical formulation, so they can share with each other. So it's an important concept. In fact, the principle of uncertainty have several characteristics. So one of the characteristics is the what we call the uncertainty pair. So for example, in the original formulation by Hankensberg, we talk about an object, distance, and the momentum. So the del x is the displacement, which means the distance. The del p is the momentum, mv. So the theory tells that you cannot 100% sure about the distance or the momentum. And all the times, their error multiplied will be a non-zero number. Again, governed by the Beauty-Planck constant. So you may ask me why? No, but it's true. All the non-quantum mechanics like that. So explained by Hankensberg, uncertainty principle is what we call a built-in property, or what we call inherent properties of every single matter. Mainly because every single matter, no matter what, they have dual property. But all the time, there may be one property more significant in some sense. Yeah, is the basic theory. So it must be emphasized that measurement does not mean we are not talking about the measurement error, but we talk about is an intrinsic error. So it's a little bit different from you have learned in high school. You measure something, the difference. No, that kind of thing. We talk about when you try to make measurement all the time, no matter how accurate the equipment is. All the time you cannot 100% say that. One of the major reasons, because as I mentioned in the last lecture, is all the time when you make the measurement, the observer itself, will affect that object. That is the basic theory. So in fact, the uncertainty principle have many applications. For weather prediction in my old job in the observation in Hong Kong, in the superconductivity, very important stuff, and quantum computing. Later I will talk about it. And of course, again, we buy this concept for study the variance market. Later on we'll talk about this. So no worry. So quantization. Quantization itself is not difficult to measure. Yes, in quantum physics, quantization is the process, that transition from a classical understanding for a physical phenomenon to a new understanding on quantum mechanics. So the most important part is we talk about is what we call object model. Say for example the Bohr model for atom. So if you study the high school physics or chemistry, you know, every single atom have the nucleus, and also within this we have the neutron and proton, right? and then circulate this. Don't know why they are electron, and also don't know why they have energy level. Okay, and each level is according to the what we call the level number, right? And every level number have the maximum number of electrons they can have. You know that the 2n minus 1, that kind of thing, right? So you may ask why. No one tell you, but I think it's true because it's some experimental facts. Okay, the most important thing is why. Okay, and what's the rules? Okay, the rule is energy are quantized in a subatomic world. Okay, and make it very clear. And the relationship, in fact, is a kind of calculation. So the most important concept is what we call the energy level. But nowadays, I can tell you that many people believe that. Okay, in fact, it's true. Okay, and fall into again some very simple equation, as you can see, very simple equation. And all the equation, one funny thing is all the time related to a very important constant, what we call the Planck constant. And Planck constant have two formats. One is the Planck constant itself, or the Planck constant offered by the 2 pi is this one. Okay, so I'll talk about this later on when we go through the Schrödinger equation again and again. Okay, you will see that guy. Okay, many times. Okay, and this beautiful equation will tell you what is the number of electrons you can have for a particular energy level, as we learned in the high school chemistry, right? So the periodic table, remember that. Okay, but of course, maybe at that time you never asked your teacher, no professor, why. But again, I can tell you that most of them don't know because they haven't taken high energy physics. But maybe even they take, they also don't know. So, but it's true again. Okay, and another important equation is the what we call the radiation equations. Is the energy for the radiation is uniquely equal to a fixed number, again, Planck constant, okay, multiplied by the frequency. Okay, we all know that nowadays, okay, for a particular kind of substance, or okay, objects, or subatomic particles, okay, the energy, okay, it will irradiate, will proportion, okay, by the Planck constant against, okay, is a radiation, which is calculated and measured by the frequency. Okay, so it's what is proportional to the frequency by the Planck constant. Okay, so it's very small in fact, but unique and important. So in quantum finance, we also borrow this concept, and we have a concept what we call the quantum price level. Okay, quantum price level. Now it becomes quite famous because we promote that for more than 10 years, and also other professors also had that kind of theory for the quantum price level. Because if you are an experienced trader, okay, in financial market, you all believe that the prices are not discrete. It will jump from one to another level, or drop from one to another level. Imaginary level. Imaginary level in the sense that it now can be only calculated by computers. I can tell you that in the old days, when we studied the technical analysis, the solving, they tell you how to do some drawing, right? To find all this subatomic system. But now we won't do so because we all believe that the whole financial world is so complex. It's impossible for you to just observe the pattern and draw the line. So why not you're using set of equation or model for you to derive all that what we call energy level. And we call this the quantum price level. Okay, we will focus on that, okay, because it's one of our major concept in the quantum finance. Okay, so another interesting topics, quantum entanglement. So quantum entanglement in physics is a very interesting topic. Is for the pair of what we call subatomic particle. No matter what, it can be electron, neutron, proton, neutrino, whatever. Okay, they exist in what we call quantum pairs. In the sense that even one of them, okay, are located in a very far distance. Okay, when you disturb one of them, okay, in terms of the spinning, okay, from clockwise to anti-clockwise, for example, the other will also do so. Even though they are separate by a very long distance. We are already doing that kind of experiment in CERN, in many laboratory. It's true for some very small subatomic particle. So you may ask why. Okay, again, we don't know. Okay, but it's true. So you may ask, we also call this spooky distance at spooky action at a distance. It's what coined by Einstein. When Einstein saw the paper from Hankensberg guys, okay, or Schrödinger's, okay, talk about quantum entanglement, okay. So what he talked about is something happened with a very long distance, and we don't know what, but in fact it's true, okay. So it's a kind of mystery. So that kind of thing can be now proved by different kinds of subatomic particles, including photon, neutrino, electron, or even small diamond. Okay, minor thing. Okay, so you may ask, how it can be used? Many applications. So you imagine if you have something you want to tell people, okay, and you want to keep it a secret. Okay, we call this encryption, of course. Okay. So how can you distribute encryption key without being transferred to that person? So if you are Ginny, you know what I'm saying is, if you have a quantum pair of key, okay, in a subatomic world, of course, okay, when one is string, another is string, so they are synchronized. So by doing so, you don't need to transmit any information. You can do the encryption. So we call this the quantum cryptography. So quantum computing is another thing. Okay, quantum computing is as you know, all the computer machine are 0 and 1 solid state, right? As we know, okay, the whole world is not 0 and 1. Okay, it's something what we call fuzzy somewhere, okay, and or what we call with different quantum state. So another kind of new generation of computer is not only 0 and 1, but many different states. So by doing so, it can contain more information, of course, and second, okay, it can model more complicated system because as I always say, all systems are not 0 and 1 kind of thing. Okay, they are very complicated. Of course, if your computer system is quantum computing system, which we can discretize in different energy state, so you can model many more compact system. Say for example, finance or weather forecasting or that kind of thing. Okay, another very interesting topic, but not my original topics, is quantum teleportation. Of course, you can imagine what we talk about. Okay, some people work on that. Okay, and some say they have some good result, but up to now, I can tell you that it's still restricted to some quantum particles. You teleport a quantum particle. Say, for example, when you saw the Star Trek, you know what I'm saying. You beam someone from one position to the other with the speed of light. Okay. Again, it's theoretically possible, but technically, it's not possible. Nowadays, but in the future you can, I don't know. And quantum finance, okay. So all different kind of things is what we call some kind of new age technologies that make use of the quantum phenomena for application, calculation, or modeling. Okay. Continue. So as I always say, subelectric good is that you and I can take a break whenever you want. Okay, and you never like to ask me, alright? Professor, I want to take a break. No, anytime you can take a break. And the most important part is if you don't understand, you can reassess. Okay, so again, see whether you understand. Again, if not, you can ask me or buy the book. So applications. Okay, there are many applications in terms of quantum theory on semiconductor. In fact, I can tell you that the most important advance in chips, solid state physics, is on semiconductor and also based on quantum theory. Yeah, laser technologies, quantum computing. The first commercial, what I'm saying, quantum computer by IBM, Q System 1, launched in electronic show in Las Vegas. Okay, 2019 January. Okay, and quantum crypto. Okay, It's a very important topic, and of course the quantum finance. Okay, and many, in fact, there are many applications. Okay, what we call the new age applications. So of course, in data editing and MRI, that sort of thing. So we are all talking about in a very minute, okay, and subatomic world happens. So second part, we talk about the quantum field theory for quantum finance, from quantum mechanics to quantum field theory. Don't worry, I just want to give you some not simple, basic overview. Okay, so especially when if you are not a major in physics or high energy physics student, okay, so you can spend some time to have a look. Okay, see whether you understand. Okay, we start on. From quantum mechanics to quantum field theory. So remember, at the very beginning, I tell you, these two are different, right? Quantum field theory, in fact, is the integration of three different theories. First, quantum mechanics. Second, quantum field theory. Classical field theory. Third, special relativity. So 3 into 1. So it's not only related to quantum mechanics, but also it has some basic classical field theory, okay, to generate the model equations. And also, in extreme case, they're governed by the special relativity, not general relativity, okay, special relativity. So we have 3 different basic components. So of course, for the special relativities, so we have to say the Einstein unit m square. Okay. So and there are so many topics of phenomena in quantum field theory, in the sense that we'll focus on the key, which is essential for quantum finance. So we won't tell you all of them because it's quite complex. But we will talk about something important for us in quantum finance. Okay, they are quantum classical field and quantum field, basic concept, quantum oscillator. Feynman diagram is just for interest, don't worry, okay? But it is worth to have a look. Feynman diagram and path integral. Okay, I will just talk about some basic concepts so that you have some touch and feel. Okay, so as I will say in this course, okay, I will tell you, okay, at the end of the course, which part are essential, need to know, okay, and which part is good to know. Okay. Good to know is different from need to know, right? And which part, okay, is better you have some idea. But if you don't have, okay, it's still okay. So example, path integral. I will tell you. Okay, so don't worry. So so first of all, we talk about the first thing. I just tell you the basic concept. Okay. So later on, when we make use of it for the calculation, you will know what we're talking about. So classical field, quantum field. So a physical field is what we call a field. Okay, it's an assignment of physical quality at each point of space and time. I don't know whether you have that kind of thinking. So example, gravitational field. Okay, by Newton, right? So if someone asks what is a gravitational field, yes, in a 3-dimensional world we see, okay, every single point, we have some quantity. That when you have an object here, the gravitational field, this sort of thing will give you some force, right? The mg, m is the mass, g is the gravitational field, 9.x something like this, right? So that's sort of thing. So in general, physical field can also be interpreted into something like this in a physical world, so that each point have a value. Okay, it can be space-time, which means integration space and time. Because for some field, it will be changed in time. So, for example, electrical field, right? Okay, something like this. Okay, and the special thing is that every single point, the number are discrete. Okay. So there are two major classical theory. Of course, we have mentioned, right? First, Newton gravitational field, G field. Okay, that's fine. We are very good field. And we have the Maxwell equation, okay, equally beautiful, and also the magnetic equation, of course. Okay, we won't go into it, but you can see all the time they are very, very symmetric, as you can see. Okay, but of course we are not in classical physics. I won't go into detail. So rather in a quantum field theory, okay, the fields are different in the sense that you can see, although the shape are more or less the same, but every single point are not discrete. They are continuous. That's what we call quantum computer, right? Okay. So in quantum field theory, particles are described by quantum field which satisfy what we call the Schrödinger equation. Of course, Schrödinger equation in fact is an equation which governs, okay, the what we call dynamics for all those quantum particles or subatomic particles. Okay, so for example, this Schrödinger equation, time dependent, and later I will show you a time independent Schrödinger equation, and I'll tell you why. Okay, so in these figures, one of the major differences: every single point in a quantum field is continuous, rather than discrete. So later on, you may ask, continuous is natural, discrete is quite hard to, what I'm saying, hard to imagine. Okay, and path integral. Okay, what is that? Just factorization, no worries. Because in this course, we won't use that for calculation because it's too complex. Okay, otherwise it's frightening everyone away. But at least you have some touch and feel. Path integral invented by Feynman. Okay, but the theory, okay, is very funny. I just want to tell you the theory. It's what we call Einstein Four experiment. So Einstein famous is what we call the thought experiment. Thought experiment is he tried to do an experiment inside the brain. Think about that. Okay, different scenario. So we start. So that kind of theory is developed by a very famous scientist, Feynman, Richard Feynman. Okay, again, of course, a Nobel Prize winner because of quantum field theory and the path integral invention. It's a kind of invention. So developed by Richard Feynman in 1948, again after the Second World War. Just okay. The path integral is a very important kind of formulation for the quantum field theory, and concerned with the direct computation of the scattering amplitude of certain interaction process. So, in order to understand path integral, let's go through what we call the standard double slit experiment. Very fun. So first of all, we have again double slit, just like the wave particle experiment. Remember that? Okay, the beam. So we have cardboard with two holes, so it become a double slit, and then we have a screen, okay, and then we have a source and two opening, O1 and O2, right? F is the screen. Okay, we start with that double slit experiment, single layer. So in the upper figure for the configuration of standard DSE, the photon particle emit from the source S at time t, okay, will go through the opening O1 or O2 because it's an object, right, and hit to the projection F, no problem, right? So for example, either go for on this path or on this path, but not both, right? So by using the superposition principle in quantum mechanics, the amplitude for the detection at the final point F by the sum of all possible paths, okay, SO1F, SO1F, or SO2F, right? Because only two possibilities. So how about we drill one more opening, O3? So it will become something like this, right? Very natural. So by using the same logic, okay, so we should add one more path, what we call superposition, okay, in order to summarize all the possible paths, right? So we have 3. So everything looks fine. So how about we drill more opening? So you can see. How about we add one more layer? Okay, so we try to summarize all different paths, okay, in a single layer situation. So we have n different paths, right? So they are all governed by SOI. I will be number opening, right? So we have n different paths. So if we add one more layers and one more layers, so it will be a second integration. So how about, so one last thing. What happens if we add infinite number of layers and do an infinite number of holes? So which means we have different paths between S and F. And the hole chord becomes a free space. You know what I mean? So by using this method, okay, path integral tells us that for the light emitted from a point source S to a final point F, the wave function detected at F should be the sum of all the possible paths from S to F exponential, right? You try to break down into different paths and add them up. We call this path integral. So if you're a genius, is how can we make use of path integral to forecast finance? Is what everything about for 1 minute. You try to generate all possibility paths from time 0 to time t. Right, add them up. So some people doing that, of course, in quantum finance. Another book, okay, super complicated because you can think about this. You talk about infinite number of paths, not easy task. So of course we have many methods to solve the same problem. Okay, so in general the whole calculation will be something like this, right? We try to generate all possible paths. Okay, so Feynman path integral formulation. So in Feynman quantum field theory, the wave function value detected from a path from point QS to a final point QF in time t, okay, is the governed by operator what we call the Hamiltonian. The equation is something like this. Okay, don't worry, I won't ask you in exam. Just show you as an example. So using path integral formulation, so we can derive it into n different sections. So we divided delta t different section n, t with n. So we have something like this. Okay, don't worry, I won't ask you in exam. Just show you how beautiful it is. In general, you can break that into n different. So, and after a bit of calculation, we obtain the famous path integral formulation of QFT. I just want to show you the ultimate equations. Very beautiful, right? So in fact, there is two ways for quantum finance. Method 1, using path integral. Okay, for my book, I'm not using that. Okay, I'm using another way, more easy to understand. But there is some way to understand that. Because that kind of method, in fact, is possible in terms of calculation. If you have supercomputers or very fast computers or computer cluster, you can do so. Because you just sum up all the possible events. So by simplification, we will have something like this. Okay, don't worry, I just show you what other people are doing. Okay, in quantum finance, but for me, we are not. Don't worry. So in general, path integrals are in the names. So how can we do that? Let me show you. Well, interest rate modeling. One important application. Well, interest rate modeling is try to use quantum field theory and try to model the past, for example, 15 years interest rate in US. Okay, because interest rate in US is very important. As you can see, US currency is one of the major currency for current exchange, right? So how can you model accurately for the past and the future years of the interest rate is very critical, of course. Okay, so we have different methods. So path integral is one of them. You can imagine because we have different history of digits. So by integrate all those different possibilities, you can you can, okay, in some sense, model the whole, okay, interest rate path by using the same formulation. But of course, it's rather complicated, of course, okay. So we can do so. And I will talk about this a bit, okay, as an introduction to quantum finance. Because nowadays we have two basic theory on quantum finance. One is using path integral by another professor, and one's for me using the oscillation model, okay. And difference is that my model is more easy to be implemented by computers. Later on, you know, because we have the workshop, right? Okay, Feynman diagram, my favorite. Feynman diagram is a mathematical one, but the most important one is try to convert mathematical equation into some kind of funny diagram or shape. Okay, I'll show you a bit. Okay, just for interest, no worry. So anyone undergrad study modern physics, okay, and computational finance must heard of path Feynman diagram. Okay, for me, just a simple 5 minutes introduction. See whether you love it or not. Okay, so Feynman tried to invent the kind of thing in 1915, 16 something, in his famous Feynman lectures. Okay, one of these is this one, of course. Okay, is the combination for electron and positron. When they come together, they will generate what we call pure energy and disappear. We call this annihilation. Okay, self-destruction. So we discuss general ideas. Okay, I just want to show you some fancy figures. Famous Feynman diagram are something like this. Just want to show you. Okay, just treat it like IQ test. No worry. Okay, if you try to spend in sufficient time on path integral, you might discover some mathematical pattern. So let me show you some funny thing. Say for example, this A, B, and C, they are the same to represent this formula. Try to figure out why. Okay, as an IQ test. And these two, okay, again represent this formulation. And that is represent that. That is funny. So there's some rules. Okay, try to spend some time as a IQ test. See whether you understand or not. Okay. Again, don't worry. If you don't understand, okay, no big deal because it's not part of our course. Okay. But if you understand, that's good. Right. So which means you have some idea on the Feynman diagram constructions. That is important. Okay, when for students taking high energy physics, good. What I'm saying is understanding of Feynman diagram can help us for formulation because all the time it's very easy for us to make mistake. Okay, but the reason why I put this is because there's another book as I mentioned, right, on path integral, and the knowledge on the Feynman diagram is essential. So what I'm saying is if you want to read this book, okay, with mathematicals, so test yourself, see whether you understand first. If you understand this, you can read. If you don't understand, don't read. Okay, otherwise it will be chaos. Okay, and quantum oscillator, okay, and quantum harmonic oscillator. Let's begin with. Quantum harmonic oscillator is quantum mechanics analog of classical harmonic oscillator. Because in the quantum mechanics, we all believe, okay, every single subatomic particle are not state phase. All the time they are oscillation or vibrating. Okay, in terms of what we call natural frequency. Okay, just like that. Okay, because this is analog. Okay, for a ball with a spring, something like this, and these are the wave equation they generate. So simple harmonic oscillator. In fact, you have learned about this, I think, in high school, but maybe you forgot. Okay. Generated by this simple equation, F equal to ma. Okay. But the difference is this ma also equal to, okay, negative proportion to the distance. You can see, which means F equal to minus kx. K is what we call the elastic constant. So it's a spring in some sense. You can imagine So that's why it's negative, because all the time is what I'm saying is the negative direction, right? If you drag this, of course you have to return. Right? Okay, K is the default constant. And the damping harmonic oscillation, the same with what we call damping factors, first order. And in some sense, we have undamped case. If you remember your high school physics, okay. Again, I don't ask you an exam, just show you, okay. What is the quantum harmonic oscillator, QHO? So QHO is one of the most important models in quantum mechanics and quantum field theory, because it's a kind of more simplified model to represent that. Okay, it's a kind of representation. So in one dimension, given by this guy, okay, not difficult, I can tell you, because more than constant. Okay, you just need to learn and also see the pattern, the relationship between the what's constant and also the distance and also the omega and mass, of course. Okay, and the solution for the one dimension QHF is important. They are discrete, and what I want to show you this one. Okay. Again, you don't need to prove. Okay, I just want to give you some facts. Okay, a quantum harmonic oscillator like forced by a spring. Okay, when you try to calculate the wave equations, they are proportional and with different energy state. So you can have some idea. Oh, that kind of harmonic oscillator, the energy level are well defined. So as an analog to quantum mechanics model, of course, it is good, right? Because our definition for quantum mechanics world is everything inside this particle. So, for example, the proton, electron, neutrino, okay, they exist in discrete state with the n number, right? What we call the level number. So this is some kind of analog, okay? Or people will call this the quantum number, of course, okay? And these are what we call the discrete energy level. So you see, even a so simple harmonic oscillator have that phenomenon. So you see, what I'm saying is it's very popular, right, in some sense. But of course, as I always say, the whole world is not so, what should I say, not so simple. So we have the n-dimension quantum harmonic oscillator. Only one dimension like this, okay, n-dimension. Three-dimension. As I always say, 3-dimension you can draw, over 3-dimension you have to imagine. Like this. Okay, jumbo, what I call. Okay, you jump. So you imagine that. Okay. The object is jump over there, vibrating, and they are affected by the field over there. So in this case, is the quantity x1 and xn will be referred to the position of each of the n quantum particles. And they are affecting each other. So it's what we call superposition, right? So in an n model, again, okay, I just want to show you the pattern. Don't worry about the formulation, I won't ask you. The energy level is something like this. Very beautiful. Oh, sorry, I'm going too fast. Very beautiful, one by one. We're all into energy level. What I'm saying is, even though so simple model, when you calculate the physical mechanics or dynamics, the energy level all the time are discrete, not continuous, in fact. That is the one your high school physics teacher never tell you, right? But it's true. Even a simple pendulum. So everything is discrete, as I always say. No kidding. Oh, quantum and harmonic oscillation. So we go from quantum harmonic oscillator to n number and then n harmonic. Okay. So what is that? Although quantum harmonic oscillator can be explained many quantum phenomena, but the whole world is not so simple, right? Simple straight, no. So all the time is what we call a damped event. So this one is a very good demonstration for a molecule, what we call HCl, hydrogen and chlorine. So this, the big one is chlorine, of course. Small one is hydrogen. So the vibration is something like this. Okay, two-body vibration. I can tell you that two-body vibration, or of course, is all very, very complex. Quantum and harmonic model. Three-body very complex, what we call the three-body model. So this kind of model, you can see the energy level is discrete, of course, right? But they are anharmonic. You can see, not linear. Of course, it's non-linear in some sense. Okay, they pack more and more. Okay, at the top. Okay, and more. Okay, widen at the bottom. Okay, it's natural, of course, right? So the formulation, okay, is something like this. Okay, the main reason why is we try to borrow this formulation, and later on I will tell you, we will make use of this concept in modeling of our quantum finance model. Okay, so just observe, okay, the meaning. So the company fund model is the cubic one with k equal to 3. So we have different k number. So it will be like this. Okay, it's still very easy to understand. Okay, with 1, 2, and 3 term. Okay, and 2 term are coming like x, degree 2, degree 3, and also 1 constant term. So products with k equal to 4, what we call degree 4. Okay, governed by this one. So something like this. Again, it's beautiful in some sense. You can see. All the time, I tell you that later, it consists of 2 portions. One, this guy, you can see. KE, kinetic equation. One is potential equation. So later I will show you. Okay, just like the potential equations. So degree 6. So you can see, no matter how many degrees it is, okay, it's still so beautiful. But of course, the higher the order, the more complex it is. Sure. Right. So that's mean the order number. Okay, so in general, okay, we can do something like this, which is what we call the 2M model. Later, I will tell you the 2M model is very important model. And the reason why we have that particular quantum finance model, because years before, in 10 years, I can't remember. Okay, I read the papers on that. Okay, and found that equations, and which match into my research on quantum finance. So I try to make use of it and try to do the calculation and come up with our quantum finance model. Okay, so all the time you read some good papers and you have some, what should I say, very new ideas. Okay, so later we'll go through this later, don't worry. Okay, but we will talk about this later, the quantum and harmonic oscillator. So one interesting thing for our course is we will base on some formulation, but we won't spend all the time or even ask you, okay, how to formulate it. No. We just show you some very important equation phenomena. Okay, because all the time, as I always say, a phenomenon is related to the equation. Because without the formulation, you don't have the phenomena. But only the formula, you don't see it is because it is showed by the phenomena. So they are the same thing, right? Different aspect. So that's why. Okay, so next we will move on to the brief history for quantum mechanics. So today, lecture we talk about some basic concept of quantum mechanics, right? Quantum field theory, some basic features. Okay, in fact, I'll recap because we have already talked about this in the first lecture, right? And just some basic thing. And the most important part I talk about is the 2 different mathematical formula, right? One is very complex, not horrible, but difficult. Path integral, okay. I also don't like this too complex. And the other, also complex, but more easy to handle. What I call the harmonic and harmonic model. Easy to handle. Later, I will tell you what. Easy to be implemented in your own program. That's what I'm saying. Easy. So it's also if something that you cannot be, what should I say, implement full computation, which means you cannot computerize this, or in other words, you cannot put into commercial or industrial or R&D. That is important, right? So we'll tell you later on, step by step. Again, if you want to learn more, okay, you can see my book, or you can have some reference. But all the time, the reference is quite difficult. So if you want to learn more, you can just download my book. Okay, it's better because my book is a bit what should I say, more detail, of course. And all the time, but in terms of the content, I tell you that they are the same. Which means if I have section 2.3, and then for the PowerPoint also 2.3. But different is that, of course, the PowerPoint will be a kind of, what should I say, extract the main concept, right, from the book chapter. But of course, the full details on book chapter. And then other difference for the book is at the end of the book, I have some what I call interesting questions. Okay, you can think about that. It's good. Okay. Because as a writer, all the time when I write something for chapters, of course we know, okay, how to make sure that you understand by what should I say, ask you questions. But different from some mathematical course, okay. Not all the time we have unique solution, so we can discuss. That is important. But of course, for some mathematical exercise, all the time is 1 or 0, right? Unless you're talking about fuzzy logic, right? We will talk about this later, don't worry. Okay, so we start in here. Okay, if you have any questions, okay, send me email, WeChat, or whatever you want. Okay, again, remember to attend all the workshop, because the workshop will tell you how to write some physical program, and the course, okay, will tell you the major concept. So, as I always say, both of them are equally important. Okay, so see you next week. Any question? Let me know. Thank you.